We saw previously how we can use information from the quadratic formula to find the zeros and the vertex of a quadratic function. It'll work for any quadratic function, although sometimes we won't actually have zeros. For example, if I had made this plus 6, the vertex would have been up higher on the x-axis. The parabola would have opened upward. It wouldn't have gone through any zeros. In that case, you can always see that this is a translation and stretch of the function y equals x squared. So if this is our function y equals x squared, and we vertically stretch that by factor 2, we're going to have the 3 points. Let me use blue chalk here, here, and here. It's going to be like this, okay? And if we then shift this graph over 3.5 units to the left and down square root of 5 over, down 5 halves of a unit, we're going to get this graph, which means, of course, a couple of things, that this graph is of y equals 2x squared plus 6x plus 2, but also that graph is 2 times the quantity x plus 3 halves minus 5 halves. Okay, because it's a vertical stretch by factor 2 on the y equals x squared graph, and then a shift to the left by 3 halves unit. So we replace x by x plus 3 halves, and then down 5 halves of a unit to negative 5 halves. So we could take this blue picture and move the vertex over to here, and we would get a picture of the graph of this function. So that's kind of an interesting connection, a little bit of an extension, but it kind of brings a few things together. So you kind of want to, if you possibly can, try to make sure you understand that whole idea. And that idea would be very handy, for example, if we had the function, what can I write that up? Just write it up here, y equals 2x squared plus 6x plus, let's make it 5 halves and 7 halves is 6 plus 8. Okay, this graph would have its vertex 6 units higher than this graph. The vertex would still be at negative 6 over 2. Negative 6 over 4, negative 3 halves. But the vertex would be at 7 halves, as you could verify by plugging x equals negative 3 halves into the expression for the function. Now, what are you going to do if you don't have the zeros to help you graph the function? Well, one thing we would know is that the x-intercept would be up here at 8. Now, that 8 would actually be too high to draw on this graph. Here we got 2, 4, we get 6, but we can't get 8 on the graph. The y-intercept would be up here. You'd be able to plot that y-intercept. But knowing this, and knowing that this function is a shifted version of the y equal 2x squared function, which is in blue. So in blue we have y equals 2x squared. We can simply take that graph and shift it. We can shift its basic points, which are 1, 2, and 1, negative 2. I'm not going to label that, but you would know that. If we shift these points, negative 3 halves of a unit, and up up 7 halves of a unit, because vertex is going to be here. The vertex is shifted negative 3 halves and plus 7 halves. We're going to get a pretty good graph of this new function. Okay, so, and if you understand that, that's a very good technique to use. I just realized that having the board over here to try to avoid some glare, I forgot to move the board back, so I was talking about something that was completely off the board when I wrote this down. Again, this expression here simply indicates that this graph has a vertex that's shifted 3/2 of a unit to the left and 5/2 unit down, which means that you have a horizontal shift of -3/2 achieved by replacing x by x plus 3/2 and subtracting 5/2 from the result. Good thing I took another look at this because I forgot to put my square on there. And this is a translation of the y equals 2x squared function here and here. This function that we just graphed would be two times the quantity x plus 3/2 squared plus 7/2. Now we got that without doing a lot of algebra manipulations, just understanding how the translations work. If you multiply this out, this expression should give you this, and this expression should give you this. So there's a little deeper connection between the shifting and stretching transformation picture and the algebraic picture.